Hello everyone. In this video we're going to be looking at the LDR equals pseudo-instruction syntax and instruction encodings in general, and fun things that the assembler is doing behind your back. So once again, this is first day lecture content which didn't get recorded properly by the ecosystem in Coombs, so here we are. Okay, so if you have looked at the echo recording or you've been following along with the slides, I believe the lecture started on this slide here, and you're probably wondering what the hell this code is doing. So what do we have? We're loading into register 0 from the program counter, +4, and we've got some $line 2 thing, and we have a word of data here, and well, hey, what the hell is going to happen when we run this? So it turns out that when we write an LDR equals pseudo instruction, we get something similar to what's on the previous slide. So, now I'll mention very quickly, if you're not familiar with your loads and stores, especially loads with offsets, so this notation here, you might want to look at the loads and stores video on this channel. Anyway, so what is our LDR equals pseudo instruction? It's a way for us to move a 32-bit number into a register, and it's called a pseudo instruction because, well, this isn't actually a real instruction. When you press the build button, your assembler is actually doing a little bit of translation from this to something else. So when we said earlier in the course the assembler just takes your assembly code and converts into machine code directly, we were lying a little bit. Occasionally it does some smart things. So yeah, this you can almost think of this as like move register 2, a big constant, but it translates a little bit differently in machine code. So here's the question: if this LDR equals isn't a real instruction, then what's actually happening on the CPU? Okay, so let's go to our Visual Studio Code, and here's an example I've cooked up earlier. And we've got a couple different moves here, including our LDR with the equals hash syntax. And we're going to have a look at what all these different things are actually doing. Now, the way we'll do this is with the disassembly viewer. So we can bring this up with our command palette, and we'll type in view disassembly, and there it is. And we'll disassemble our main function. So that means anything between, well, main and I think .size main should get disassembled properly. Now, if you don't have this line here, the .size main, your disassembler will not work correctly. So let's disassemble, and we get this view here. Now I'll just drag this over here so they're side by side, and I'll line these up. Alright, here we go. So on the left side of the screen we have our main.s file, which we wrote, and on the right we have our disassembly view. So the disassembly view is a human-readable view of the raw machine code that is uploaded to our CPU. So if we look at this line here, we have a no-op, and over here we also have a no-op. So as the lines are directly lined up. So this line over here is this line over here, etc. So what do we actually have in our disassembly view? This is the memory address of this instruction here, and this is what the instruction actually is. So we have memory address, raw machine code, and instruction. So pop quiz trivia question: how many bytes does our no-op instruction take? The correct answer is 2, as we can see here. Our no-op instruction starting at address 1C8 is 2 bytes. Okay, so let's step along. Also, our debug stepper will also go into this view for us. So we'll bring up our registers. So we're still running the same program here. It's just put the little thing in this window instead of in this window. Now, what do we have here? We have a few different moves. Our first two moves are both moving a 8-bit number, 0xFF, into a register. So let's just do these quickly. We have R0 and R1 both contain FF. Now you might be wondering why my move assembly instruction here has been translated into a move.w. Well, it turns out if we go to our handy dandy reference manual and look here, this is our move.w encoding. So it's 32 bits long, just like in a disassembly view, and it takes an immediate number and a register and smooshes it all around, and that's what we get. You might be wondering why this move, which is the same number, has a 16-bit instruction encoding. Well, it turns out that our short and compact move has to be a move S. There are many little interesting niggly facts about the ARM instruction set, and this is one of them. So to get the short encoding for moves, which fits only 8 bits of number, we have to make it a move S. Now, of course, as well, if we want to move a bigger number, so a 16-bit number, then we must use one of these wider move instructions. So in this case, the assembler has used a MOVW. We have MOVW here. So what MOVW does is it takes a 16-bit immediate value and a register. And the 16 bits get put in the instruction, 8 bits here, 3 here, 4 here, and 1 up here, and then the CPU smooshes them all together with this, so it concatenates them together, and that's where our 16 bits go. And our mov.w does a similar thing here. Okay, so the main takeaway here is that our assembler will take, the same or very similar instructions and encode them all very differently. And if you're trying to optimize your code for size, for example, then it might be very handy to know that a MOV-S is only 2 bytes in memory, but any other kind of MOV will probably get encoded to 4 bytes. Okay, so let's get back to our LDR equals half word. And we can see here that what was an LDR is also an LDR over here, but it looks a little bit different. So you might remember from the lecture slide that this familiar looking thing. So let's have a look at what it's actually doing. We're loading into register 3, which we have here, but we're loading from the memory address that is the program counter plus 4. Now that's not quite our 0xdeadbeef here. You might also notice that this is only a 2-byte instruction, and deadbeef is a 4-byte constant, so there's no way that we can fit the constant into this LDR, so it's actually doing something a little bit different. Now, if we remember, the program counter is always the address of the next instruction the CPU is going to execute. So when the CPU does this instruction, the program counter will be equal to the address of the next instruction. So when the CPU does this LDR, the program counter will be 080001D8. So we'll be loading from that plus 4. Now if we count in hex, we go from 8 to 9, A, B, C. And our disassembler actually does this addition for us, so that's the address we'll load from. Now, if those of you who are following along at home might notice, that is actually very close to this address. In fact, that is immediately after this address, because we have 1D, 8, 9, A, B, and then C is immediately afterwards. So we're loading from somewhere in memory straight after our branch.main, or our b.w instruction here. So let's do this LDR. And we can see here deadbeef is loaded. And now let's have a look in the memory viewer. We'll start at 0x080001C8. So we'll start our memory viewer at the beginning of our program, and we'll load the first 100 or so. And I'll just bring this over here. Okay, so let's look at our address here. 1DC. And here we go. Here's our deadbeef in memory. And we can also see here that this is immediately after our program here. So 00BF, that's our first no-op, and our second no-op, we have our mov.w, our mov.s here, our second mov.w, our LDR R3 PC plus 4, and our BW. There we go. So that's all our program there, and then we have our dead beef. Cool, hey? I think it's pretty cool. So essentially what our assembler has done, I'm going to pretend I'm the assembler and I'm looking at this assembly file and I see this. And what I do is I go, right, so I'm going to go LDR R3, and I know the program counter will be pointing at this instruction here, and because I'm a smart assembler, I know that's a 4-byte instruction. So I'll go 4 bytes forward from that, and then what I'll do is I'll pretend I'm an assembler, and I'll go dot word 0x DAD beef. There we go. So PC will be pointing to this instruction. I know it's 4 bytes, so I'll jump over 4 bytes and then I'll load a word from there. And that'll be our dead beef word here. So you might call this a program counter relative load, because we're loading relative to the program counter. And as you can see, this is also a very nice small instruction here. One last thing before I wrap up the video. Let me comment this out. Say we load into a register a label like main. So let me reload my window. Okay, so say we load a code label into a register. We know that LDR3 with this equals is a pseudo instruction. So let's see what this turns out to be. Oh, excuse me. Line 16. Okay, I'll just comment this out. Don't know why that was unhappy. So once again, disassembly view, main. There we go. So it turns out when we write a load with a code label, it's actually doing the same thing. It's putting our code label, so a memory address somewhere in memory, and doing one of these handy dandy relative loads. I'll just find that. Here we go. So if we look in 1DC, there we go. We have the memory address of our main label. And if we look up here, that's our first no-op, because if you remember, code labels are simply the address of the first instruction after them. So there we go. Our LDR register equals label is actually the exact same pseudo instruction as when we do an LDR equals constant. Okay, so I hope this video has been helpful to you, and I do understand this is going to be a bit of a confusing concept. If you do get stuck, then what I would suggest, first just try watching things again. Do try just experimenting with things on your Disco board using your memory viewer and your disassembly viewer. Something else that you might find helpful to work these things out is just writing stuff down with pen and paper and doing the instructions one by one manually. But yeah, so this has been LDR pseudo instructions.